So today we are going to continue from decision tree. Or, so we are going to continue from decision tree, and then we will be learning something called ensemble learning, the various technique. Great, great. Should we start? All right. A quick recap. So what we have learned in decision trees, and the first thing is we understood that decision tree basically can represent a complex logic. It could be for classification or regression. So decision tree could be used for either. Now, so here we took an example of decision tree, creating a decision tree based on the petal length and petal width. And afterwards, we were able to create this kind of a decision tree. All right. And we learned something called Gini impurity. And the Gini impurity was basically representing how impure a particular node is, as in if it contains multiple classes, that means it's not pure, as in it can't classify clearly, but if the Gini impurity is 0, that generally represents that it has only one class in it. Okay, so that was basically a quick kind of a cost function for each node. All right. So further, the way we can visualize it, if we have two features, petal width and petal length. So first for the first Z node is not first Z node, first node in the decision tree, that the higher level is basically dividing at some point. Then the left one is pure, so as in the decision tree here, the left one is pure because Gini value is 0, so it doesn't get further divided, while the right one, which is not so pure and is divided further, but this time with the width. And it's not necessary that it would be divided by width, it could be divided by length again. Okay, so then it gets divided by width, and so on. Okay, so that keeps on going until either the max depth is reached, or we have found the Gini impurity as 0 at every leaf. Okay, so the formula is this for computing Gini impurity, and we went through the understanding of it. We also understood what is white box versus black box and the reasons to choose either. All right, so let's just go ahead, and here we talked about how the decision will happen, and then we discussed the cart algorithm. Cart algorithm basically tries to split on the basis of feature k and a threshold tk, such that we get the purest subset on both sides. So the way it happens is, imagine that the horizontal line, let me just go with this diagram. This will give you a better result. Okay, it'll give you a better idea. So okay, so what it does is the algorithm, imagine that this side, okay, let me take a snapshot again. Okay, so it'll first try to draw here one region boundary, compute the Gini impurity this side and this side, and so on. Okay, so I think I can do a better job myself, right? If we had, let's say, these are our axes, here is our petal width, and here is our petal length, or the other way. This side is say petal length, and this side is petal width. Okay, so what it is going to do is it is going to first compute this as in Gini impurity this side and this side, and if that doesn't work out, it is going to move this ahead, and this is our threshold. Okay, and compute the Gini impurity on both sides. If that doesn't work out, then again it's going to draw it somewhere, and so on, right? So this way it will, and afterwards it'll also do this. It'll also draw this. Okay, so the same thing it'll do. Let's say it'll put a line here, compute Gini impurity this side, compute Gini impurity this side. If everything is good, it looks as in it has hit the minimum Gini impurity, then it will stop. uh, Not stop, it will basically finish the entire iteration and find out the location where it gets the minimum Gini impurity, and that's what it is doing continuously. Okay, so again, in this example, when it is drawing the line, all it is trying to do is how many, how pure is this side? How are we able to separate these two? Okay, so imagine that there are some data points, some, let's say, let's say there are some elements like this. Okay, so there are two flowers I'm trying to represent. So like this. Okay, so it is going to draw the line such that both sides are most pure. Okay, so let's say this would be a really pure one because only one has gone this side. So it'll compute this, it'll try to draw all these and then see. Okay, it could also come up, the only thing is it'll be only variations of either W or L. It won't be something like a line like this. Okay, so it'll be basically the orthogonal ones. It varies only L and W at a time and then tries to find out. Okay, and once it's done with drawing this line, then it will further try to divide this, and then probably next time it's going to divide it like this. Okay, so basically it does the iteration, it keeps on recursively splitting the space by the line so that it can prepare the model. Question from Kamal: decision tree will always have the boundaries in straight lines. That's right. Okay, all right. But if you go more granular, it would become the more it grows granular, it can actually cater to both sides. And in a way, Kamal, it's a very good point. In a way, that's also the instability of the decision trees. That's exactly the problem with decision trees, because if the data orientation shifts by slight angle, by a tiny angle, the whole predictions basically go haywire. Okay, so a question from Bintao: why does not this command iris.head work? Because I think iris is a dictionary, right? So iris.head is there is no function called head on top of the dictionary. Okay, All right. So we talked about the cart model. I hope the cart algorithm is clear to everyone. A question from Noor: does it not sort the dataset by the feature in order to divide, as in binary search? The sorted list is required. Yes. So if you basically, it internally sorts it so that the computation becomes easier. Computation becomes easier, and as in it is easier for it to search quickly. So there was a point that we discussed yesterday, that in case you sort the data upfront, it becomes easier for the cart algorithm. Just that you have to tell the data is already sorted. Okay. All right. So yes, there is a parameter for that. Okay. And yes, so that's what we discussed yesterday. And basically, training algorithm compares all the features, and the result in the training is in a training complexity of this one. Okay. Now, next is the other measure that people use is also entropy, and the entropy basically has a similar formula whereby each of the p, the probability, or you can say the fraction of a particular class, is multiplied by log of itself and summed up. Okay, so this is the entropy. Entropy is how much is, it's similar to impurity. How much is our data more distributed? So the more is the distribution, the as in how many classes are there in the output. The more are the number of classes, the more is going to be the entropy. Okay. And why negative? Because the fraction is lesser than 0. Therefore, log of this fraction is going to be negative, and hence overall the number is going to be positive. All right. So if you have more number of fractions, then if this is, say, fraction is how should I say? So if the fraction is 1, then this won't contribute to this. That means the entropy is going to be 0 for that one. As well as fraction is 0, then also it's going to be 0. And therefore, therefore, this would be very small if the data is less distributed. Okay, because this will become 0 in case either p is 1 or p is 0. All right. So in that case, the impurity will be. So yes, I is the yeah. So I is the instance. So I is the class. Okay. If there are n number of classes, so we will do this for each of the class. Okay. I is the I at the ith feature. So at the ith position. So when I'll say, so this is basically the I here is hi, right? It's a measurement of entropy. So I is the point at which we have drawn the line. So there could be many such lines, H1, H2, and so on, and we are computing their entropies. While K here means that K is the class. So we're going to compute the fractions of each class on on either side and then sum it up. Okay. So this is for one side, and the similar is going to be on the right hand side. So I is basically probably the I here is the left or right actually. Okay, the left or the right. Okay, so here the k is for each feature, meaning k is varying from 1 to n, as in this is the class. So k is going to be 3, 1, 2, 3, like that. Similarly here, k is going to be which one are we talking about? Depth to left node, this one. So this one is 0, this is k0, k1, k2. All right, that's what is k. While the hi represents either the left one or right one. When it draws the line, it will compute h for the left, h for the right. Okay, good question. So Gini impurities. So question from Noor, so max of I will always be 2? No. The max of I will be total number of classes. Here, since we have only 3 classes, okay, sorry. The I as in the left and right. Yeah, in this case, it will be only, in our case, the one which we are talking about. So in decent trees, H will be computed for left and right. So I think I'll be 2 only. Okay. There'll be left and right. That's all. Okay. So for each line we draw, so for each line we draw, what we are going to do is we are going to compute H for the left, H for the right, and then compute the summation of the two. Okay. All right. Then we compute the summation of the two, and then see where is the minimum impurity. Okay, where is the minimum impurity? All right. So then we talked about regularization. Regularization as in we need to fine tune we need to control the degrees of freedom. Otherwise, it would try to overfit the model. Like in this case, it, it even further divided here. Okay. So if we say that don't divide after the minimum number of leaf node have achieved, then it will stop dividing here. So those are the various parameters that you can control in order to regularize the decision tree. So the moment we said minimum sample leaf must be 4, therefore here this one did not divide further at this point. Similarly, the case here, it did not divide this further. Here it has tried to divide earlier, then it has stopped dividing. So by controlling the parameters, controlling the hyperparameters, we can always regularize our decision trees instead of, because decision trees have a tendency to kind of memorize or overfit the model. Okay. Now, then we talked about the regression with decision trees. Decision trees are also capable of performing regression tasks. So let's build a regression tree using the scikit-learn's decision tree class, training it on a noisy quadratic data. And the way we did this is using the decision tree algorithm. Okay. Now, this is what we were discussing yesterday at the point where that's right, Kamal. If we do not regularize at all, then will a decision tree always overfit to a zero error in the training data set? Yes. Okay. So there could be a scenario while it is drawing the lines here, when it is drawing the lines, okay, that it can't divide further. Like in this case, um, there could be a scenario, there could be a point where there is no line that divides it perfectly. For example, here when it was dividing, there is no way that it can divide with a single line and still have zero error, right? So this time there is zero error this side, but there is some positive error on this side, right? So it will go further and divide it. Okay. Now this side is zero error, this side is zero error. So it will keep on dividing until it reaches the zero error if we leave it unconstrained or do not regularize. So it'll kind of memorize the entire data. All right. Question from Kamal is, can you put a circle in the earlier diagram at the center of the four triangles, like here? Okay. Yes, Noor. There is a max depth restriction which will stop the decision anyway. But if we leave that unconstrained, if we say that max depth is say 1,000,000, then it will kind of continue to divide the space until it memorizes the entire, until it represents the entire data as a tree. Question from Kamal is, now will the random forest, are we talking about, okay, will the decision tree create a pond division not continuous? Okay, do you mean that if we have a round circle here, okay, so what will happen? All right, now, so let me just delete this line. Okay, so imagine this. Let me also remove these points. Okay, all right, we have, let's say, correct? Oh, zero here, O here, and triangle here. Now, let's say it is dividing it and it's trying to compare whether to divide it here, here, where is the minimum impurity. Okay, so also it'll try to draw the line like this. Okay, and basically in the beginning, probably this is the most pure to me it is looking. We'll first try this. Yes, go ahead, unmute.
Can you hear me?
Yeah.
So I'm saying that just let's imagine a hypothetical scenario in the same diagram where there are a lot of circles on the left, and then
Okay.
there's a layer of triangles which form some sort of a you know empty square, two layers,
Okay.
and then there's in between a lot of circles,
Okay.
and then on the right hand side lot of circles.
Okay.
Right. So, I mean, up till now, whenever we've seen a decision tree, it always splits into two. So it always has a continuous. I mean, if you go back to one
Hmm.
of the slides that you've made, even when there was an anomaly, it tried to, squeeze it with yeah, this exactly. It's trying to squeeze it with the continuity of the. I mean, there are, for example, in one country, a state cannot lie within a state.
Right.
So, can a decision tree create a state within a state?
It does. It does. I'll show you. So basically, it'll keep on, no matter what happens, right? It'll keep on dividing it further, 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 further like that. Okay, it can keep on basically going divided all around. Is that your question? No.
Yeah, 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 exactly. If we'll do that, then the final diagram can
Mhm.
have a green surrounded by a yellow.
Can be a green. Okay,
Yeah,
can be a green.
green surrounded by
Yes.
yellow.
Okay, okay, okay.
Can that happen? Is my question.
It can happen. It can happen theoretically. Okay, so as in, let's say, you saying that imagine that circles were in the round and the triangles were in the middle.
And then there was one circle in the middle of all the triangles.
Okay, so let's say here, let's say more are there around it, correct?
Yeah.
Like this,
Yes.
correct?
Yes.
So imagine that we are kind of preparing um, computing impurity. So it'll kind of maybe draw it here because this one looks more pure, maybe this one,
Mhm.
okay, and it'll further divide it, okay, and it'll maybe draw the other one here.
Yes.
These ones are two leaves,
Yes.
and then further it will kind of divide this one from here to here, or something of that sort, or maybe I don't know which one, which Gini impurity will be lesser.
Let's
Okay,
imagine on the top.
so one here, this one, it'll make it disappear afterwards. It'll also further divide it here, and then it'll kind of divide it here, and maybe it'll divide somewhere. Yeah. So basically, it'll keep on.
So here then the circle one. Uh,
Mhm.
no. Can you put two triangles on the left and right of the center one?
Two triangles to the left and right. Okay, just a second. So here,
Yeah, yeah, yeah.
okay.
So then, I mean,
So then it'll basically try to divide it here, or
uh,
maybe here,
and then
and then basically this could be one of the solutions. So it will imagine that. So your question for further would be that what if there was a triangle here and triangle here, right?
so will it try to have a continuity? I mean, or is it okay to not have a continuity? I mean, a simple way to imagine it is: can there be a state
Mhm.
within a state?
Yes. So so continuity. What kind of continuity are we talking about? Continuity of what?
I mean, if you go back to the
So,
slide,
you mean to say that can there be something
yes,
of like this?
yes, yes, yes.
No, actually, it'll basically divide it further like this, okay, and further like this.
So
So
it'll
the
keep.
the line will always touch the edge, the boundaries.
It has to be a continuity.
Yeah, yeah,
Okay. Yeah.
okay. So
Okay.
because its sample space is kind of dividing it. So threshold, the line that you see here is nothing but a threshold that we have decided here. This is that threshold. This line, the vertical line that you see here, is nothing but this threshold that we have decided. Basically, this feature. It's basically this vertical line. Okay.
Mhm.
All right. So good. So basically, this line, right? What does it represent? It represents that we first divide the data with this line, then this line, then this line. So it's basically a tree having many, at least 4 or 5 decision points. Okay. Good. Good. Very good question. All right. Wonderful. So this was an example of how would the algorithm work, and I think I hope that everybody got the idea of the CART algorithm by now. That all we do is keep on dividing the space by horizontal or vertical line. Where why we are saying horizontal vertical, because we are saying that we're choosing a value for a feature. Okay, if there are 1,000 features. So it'll iterate over each feature and draw the line in that dimension. Okay. So yes. So notice how the predicted value for each region is always the okay. this is what we were talking about. So decision trees could also be used as a regression. And how does it work? The way it works is at every point of time, it's going to compute the average of error. Okay, let me just take it and okay, wonderful. Great. So let's just log into CloudX Lab, take a look at our notebook. A question from Vinta, have you committed your changes in the console? I think I did. I did yesterday. So, all right. So here, this is the one that we did. Okay, let me just see the decision trees. Yeah. So here the history would show, it shows that the image creation from the notebook, drawing graph within notebook. These are the two commits that I made yesterday. You'll have to do pull. And in case you have made some local changes, you might have to override them using git checkout. Okay, I clicked on the history. I clicked on this history and it showed me. Okay, now the question from Anur is, what's the difference between the decision tree and card? Card is nothing but it's the algorithm. Card in yeah, card is basically the classification and regression tree algorithm. Okay, so there would be definitely other algorithms as well, and for training the decision tree. Okay, all right. A question from Vinta, git pull doesn't work. What error are you getting, Vinta? Do you want to? Okay, good. All right, great, great. It's working now. All right, now let's be here and try to log into my Jupyter. All right. All right, I've run everything all above. Okay. Now the next thing, what we are doing here is, this is the regression part. What we are doing is we are importing NumPy, we are importing the PyPlot, and then we are setting some seed. Then we are saying that there are going to be 200 instances, and we are generating random X, okay, the random instances. Then we are generating the value of target. The target variable Y is equal to this. So we are adding some noise to it. Okay, we are adding some noise to it. We could also simply just add the noise here. That will be more clear. Okay, so we are saying that y is equal to 4 times of x minus this square. Okay, plus some noise. Okay, and then we are, once we are done here, then we are, okay, then once we have created, here we are creating decision tree regressor. Note the point. So it's a decision tree regressor. Okay, earlier it was decision tree classifier. Okay, so you can see that the decision tree classifier. So there'll be a decision tree classifier. You can see that the decision tree classifier works in the same way. So the terminology everywhere is consistent. Okay. So here we have created the instance of it, and again the maximum depth we have kept as 2, and then the random state. And so this is again a hyperparameter. In order to get our consistent results, we keep the random variable not so random. Okay, so right now here what we're doing is we are creating two trees, tree regression 1 and 2. Okay, one with depth 2, another with depth 3. Okay, and then we'll be plotting the same thing. So let me run it. So here after fitting, it can do the prediction. Okay, it can do the prediction. And where did we do the prediction there? Yeah, here. All right, so you can see that here, this is how the tree looks like. So if your data was like this, it's basically a curve. What it did was it drew these lines which are closest to the center of each section. Okay, it drew these lines which was closest to the center of the section. So at the depth 0, at that higher level, it drew this line, then this line, then afterwards it drew the depth equals true, right? Depth equals, yeah. So first this line, then this and this line at the same depth, and afterwards it drew other lines. So it basically kept on drawing the lines which are closer to the center of the data. Okay, so you can see that instead of drawing this straight line, it is drawing these kind of stairs. These kind of stairs. So it will try to fit kind of stairs into this kind of data. Okay, so since it has done, this is the decision boundary. If you say what is the value of y at this point, y at this point, so it'll draw the line till here and say that okay, the value of y is equal to this height. Okay, similarly here, what is the value of y in case of x? All it will do is predict this value for all the values in x in this range. Okay, so for all values from here to here, the value of y that it is going to predict is equal to this. Okay, can we just give it a shot? Okay, here we could say, So we have two. Okay, we can say tree regressor one dot predict. Okay, so we could say there are two tree regressors, right? So I'll say tree regression one, and for the value of say, okay, this is going to be same in both the cases. Let's say point. This is how much? This is 0.1, 0.05, 0.04, 0.004, right? Okay, so some kind of this. So you can see that it has predicted this as the value, this as the value. What if I predict, if I ask for say, instead of 4, I say 3.8. Will it be, okay, so we say 4 and 3.8. So you can see that for both 0.04 and 0.038, the value of y is exactly same. So this is the height, this is the point here. Okay, now it's similarly the case if we say tree 2. Okay, we have created basically two trees. Okay, so here 0.004, 004 this, and the value is here. Okay, is it clear to everyone? A question from Noor is it possible for you to increase the depth and run it again? Definitely. So let's just compare this time the 3 and 4. Okay, let's just compare 3 and 4. Okay, you can see this is now max depth 3, this is max depth 4. Because these labels are hard coded, that's why it is showing us 2. Okay, this is for max depth 3, this is for max depth 2, because we have a hard coded them. All right, and these labels are also kind of hard coded. All right, so this is 3, this is 4. Okay, if we put 3 here and 4 here. Okay, can we try a little more? What if the moment we increase the depth, it's going to be, say I say here 5 and it's 7. Let's say 8. Right? Do you see that? It's just going so closely and considering all the outliers in that. Okay, the moment we say 5 or 8, then it does basically very fine work. All right, back to 2 and 3. Great, great. So what we learned was that this is how it works. Okay, a question from Kamal is, can we try removing the depth? Okay, do you mean that what if we do not specify a depth at all? Okay, you can see that it has basically it has basically gone with some default depth. Let me just see what is the default depth it has done. So tree two, let's just take a look. Okay, so all right, we provided none. All right. So it has basically, it kept on going till some point. I think it has gone to, okay, why did it stop? And let me just see. So here it says that minimum sample per leaf is 1, minimum samples split is 2. So it would stop at the point where samples to split is lesser than 2, okay? And that's what it has done. At the point where the samples to split were only 1, it did not split them further. That's what it did. So none is actually going unlimited, and it is doing that. Okay. All right. A question from Kamal is, I removed the maxed up parameter only and tried now. How do I know what was the depth it used? Okay, so it kept on going till one of these parameters were met. Okay, all right, because it can't further divide if there is less than one sample, less than 2 samples. Is there a way? I was also trying to figure that out, but there seems to be once we draw the tree, then we will be able to see the depth. I think there would be a way to compute the. Is there a okay? Get parameters. No. Okay, so we have class weight, classes, decision tree path, feature importances, fit, max depth, max features. Max depth is 0. It's not giving anything. Random state and tree. Okay. Yeah. Using this, you can find Kamal. Okay. So it went up to 15th depth. That was the depth. All right. Thanks for the question. I got to explore this more. All right. So you can see that the tree is the one that is the model generated. Okay. Great. Great. So yes. All right. Question from Noor is the max depth of tree. If none, it will expand until the leaves appear or until all leaves are contained with this. Good. Thank you, Noor, for that answer. Okay. Okay. Great. So yes. So what we did was we did tree underscore and all right. So notebooks tab completion is really good. It kind of helps in many ways. Otherwise, we'll have to keep going to the documentation. Good. So what we did was we basically used the tree used the decision tree for regression, and we learned that it kind of draws these decision boundaries, like decision boundaries. It basically draws the labels. Okay. Okay, so a question from Kamal is, why is printing tree regression 2.max depth? Because the reason is that is the input that we have provided, and since that is none, okay, this max depth here is actually the parameters that you passed, not it generated. The one it generated is under the tree, okay, and we passed none. All right, wonderful, wonderful set of questions. So we could again prepare the chart the way we did earlier. Yes, okay, we did this part yesterday. Okay, and we can prepare these values. All right. So now the the cart algorithm here works in the same way. It's just that on what basis should it draw the line? On what basis should it compute the cost is decided by a different function. Here what it does is it computes the average, the mean error on the right, mean error on the left. Okay, and then sums up all and finds out which one is giving the smallest result. So it's a weighted mean of the two errors, error on the left, error on the right. Okay, so it'll draw a line y. Okay, so basically it'll draw a line at certain point like y. Okay, and yeah, so right. I got the answer. So what it does is it'll draw a line like this. There'll be some data points on the left, some data points on the right. Left and right is same as above and below. Okay, so let's say we drew this line and we found out what are the numbers below and what are the numbers above. Okay, now for both of these, it'll compute the average. Okay, compute the average here, the way it's computing. Okay, and it's compute the average of both the sides. Okay, once that is done, once the average of both the sides is done, and then it will subtract each of these values from both sides. So it's kind of finding the mean error on this side, then this side, and then computing multiplying the total instances on the left and right and summing the error. So when the error is lowest at the point where the total error of left and right is lowest, that is the line that we should be trying. Okay, that is the line we should be trying. So basically, the minimum error, let's say it drew the line here instead of here. What would happen is on the left, this left error is 0, while right error is the average. It'll basically find the error of the right side and then compute it. Okay, so since the average value on the right side is going to be higher because of this, so that's fine. Okay, let me try to explain again. So all it does is it tries to draw a line at various points. It tries to split the data such that the mean square error is minimum. The mean square error of the left and of the right is minimum. Okay, so first it finds the average of the node, and okay, and then mean square error. It'll basically it'll find the mean of this one, mean of this one, subtract each value from the mean, square it, and then sum it up. Okay, so this way it'll basically find whether this line is we are drawing a line such that the mean error on both sides should be very minimum. Okay, if there are too many records on one side, I think I can explain it better with my drawing. Okay, okay, let's just take a point where, okay, so we have two data points, one here 1 here. Okay, and we have to draw a line such that the mean square error on left and right is same. Okay, let's say we draw here instead of drawing in between. Okay, now let's say the distance from this is say 4 and this is say 6, and we have drawn the line at 3. Okay, now the on the left hand side the mean error is 0, so let's just ignore it here. Now the error on the right hand side, what is the average of 4 and 6? The average is the y cap is 5, right? The y cap is the y cap is 5 because summation of all y's divided by total m, right? So 4 plus 6, 5. So now the MSE on the right, MSE of right is how much? Summation of average minus each value and square of it. So 5 minus 4 is 1 plus 1, right? And yes, so it's going to be 2. And now the now the if you see the way so the overall error that we will get is how much? The overall error that we will, where did it go? Not here. Okay, so the overall error that we'll get is the fraction of the values on the right, and fraction of value multiplied by that. So we are going to say total error, MSE total error, right? Or we can say J whatever equals the cost function equals 2 is the error on the right hand side, while the left hand side there are 0 elements, so we are saying 0 on the left plus right hand side 2 by 2 2 by 2 multiplied by 2. Okay, so 2 by 2 multiplied by 2 is how much? 2. So the error is 2 in this case, since we have drawn the line here. Okay, now if imagine that we drew the line here like this. Okay, so let me, instead of doing that, we'll just draw it like this. Okay, all right, so can I delete this part? Now for this decision boundary, for this the split, the average of y left, and y left is going to be the average, the y is 4 only, right? 4 because there is only single element. Y of this is 6. The MSE is 0 on left, correct? Let's say we drew it at 5. MSE here is also 0 because there is only single element. And when you sum it up, even if there was one more point here, the MSE will be overall very small. Okay, so now if you see, the overall error is actually 0 by just moving this from here to in the midway. Okay, so even if there were multiple points, we can prove that by moving this decision boundary to the middle will reduce the overall error. The more middle it goes to, the smaller will be the error. Is the algorithm clear to you, everyone? Okay, so the summation of errors on both sides goes to small number once we move the boundary from here. Let me minimize this. Okay, from here to here. Here the MSE was overall 2. The error of this one from the center, and same here. But here it is 0. So the MSE here is going to be 0. All right. Now, Abhinav, Balaji, Binta, Gigi, Noor, Pavan, Pratik, Ross. So we first drew two lines, one here at 3, other at 5. The one we drew at 5 gave us a smaller error. Therefore, that will be considered as a better boundary. Okay. Now, going back to the visualization, that's what it is going to do for all these numbers. It's going to draw these lines everywhere such that it splits this data so that the mean error on both sides, the weighted mean error of overall is low. Yes, go ahead, Kamal. Correct, correct. That's right. That's your understanding is right. In decision trees, the end outcome is not really a formula how all other regression algorithms gave us in terms of beta and x. Okay, it is just an in-memory label. Very good question. Very good point. Now, that's what we're going to talk about afterwards. Quickly. So at first, it might look that in the real time, what would happen is when we are going to predict something, it is going to go through the entire tree and then give the outcome, right? Instead of just giving the value upfront. So, so unlike say linear regression where we have all the betas figured out or thetas figured out and the lines and the hyperplanes already figured out and when we want to predict, it just multiplies those things and gives you. While in case of say a decision tree, what happens is when we say give me the outcome at zero point 0.7, so it'll go through the nodes of the tree and then it'll go through the nodes of the tree and give you the outcome. Okay. Now, in this case, there are a depth of 15. Okay. So comparison in the worst case scenario in our example, the one which we talked about just now, what was the depth? Depth automatically it figured out. Even in this case, there were depth of 15. So at max, there will be 15 comparisons at the time of giving the result. Okay, so the depth basically then if the more the depth is, the more is going to be the time taken to giving the prediction. Okay, is that clear? So if you have more depth, the number of comparisons it would take to give the output is equal to the depth. Okay. Predicted value in the decision tree will always be on one of the leaves. That's right. Good. All right. Wonderful. Okay. So again, just like classification does, decision tree for regression is also prone to overfitting. Without any regularization, the model may overfit the data, just like here. It has, in our case, when we left it without max depth, it kind of overfit and memorized everything. Okay, it kind of memorized everything. So if we let's say, what was the data point that we have? Let's say X, let's say for this value, 0th value, right? right? So let's say we have these two values, right? Print x0 and print y0. Okay, so for x equals to 0.37, 0.37, 0.37 somewhere here. The value is say 0.005 somewhere here. Okay, so if you look at this data, this here it has kind of memorized entire thing. So if we say predict, okay, predict for this value, it will give us really good result. Okay, all right, let me just copy paste it. Okay, you can see that it has basically this one has memorized everything, and if we just so it has kind of memorized everything. Okay. All right. Before moving further, let me answer Noor's question. How does it know that it has to divide at point 2 in the first iteration? First point 2 at first iteration, you know this one. So all it did was it computed in the beginning for this data that you see here. It first drew this line, found the mean error of this side, mean error of this side, and then computed the weighted one. So it basically kept on drawing these lines like this on left and right, and kept on computing the error. That's what it did, and found that at point 2 the error is the lowest. Okay, so first it must have tried point 1, point 2, point 3, point 4, and so on. It must have tried all of that. Okay, good question. All right, now so that was one thing I was explaining. So without any regularization, the model may overfit the data. It kind of memorized everything. Overfitting means it'll perform perfect. It will give zero error on the input data. While running on the test data, it would give a huge error. So that's basically overfitting. Okay, so without any regularization, you will get the above kind of model. So this is what we did. It is obviously overfitting the training set very badly. Okay, so by just setting that minimum sample leaves that it needs to use is 10, is much more reasonable model. Okay, so you can always regularize your model by using these parameters by constraining the degree of freedoms. So here, when we said minimum sample leaf, this is how it looks like. Okay, so this was the regularization part. Now, a very important question that has been already brought up by Kamal and others. There are some demerits of decision tree. Decision tree loves orthogonal decision boundaries. Okay, the decision trees love orthogonal boundaries because they split on perpendicular axis. So if our data is slightly twisted, okay, data is slightly twisted, it makes them sensitive to the training set. Okay, so the rotation matters a lot. Okay, they are sensitive to small variations of training data. Okay, now the other part is that the recent trees are very sensitive to smallest variation in the training data. Okay, just like because the recent tree is specifically in regression as well as in classification, both the cases, the formula that they use for finding the say minimum error or minimum Gini value, in both the cases, what it does is both Gini value as well as mean square error is sensitive to the new records, and therefore addition of new records would change the decision boundaries. Okay, so these are basically the two main important demerits. One, it's very sensitive. The model is very sensitive to small variations. Second, it is basically it is very sensitive to rotation. Okay, a question from Ross is what does sensitivity mean for cross validation? Okay, so let's take a step back. So what does this sensitivity mean for cross validation? So the okay, so in case of cross validation, since the variation the yeah, so okay. Okay, so in case of cross validation, we would have many decision trees tested on the same tested on parts of the same data set. Therefore, you remember in our first chapter that even though the decision trees memorized everything until we did cross validation. So let me take a step back and try to understand the question. So what does the sensitivity mean for cross validation? Okay, so basically there'll be a variance, there will be a difference between the various subsets. So if we take the same data, take its subset and try to train decision trees, the results could vary a lot. There would be a huge variation between the various folds of the data, right? So yes, so that's what it means. So it's because of sensitivity towards rotation and variations of data, the results in case of cross validation would be varying. There will be a difference between one set and another set, and the difference is going to be huge. Okay. The difference is going to be maybe huge, not huge in terms of really big, but it'll be like more than 2 to 3% sometimes. Another based on the data. In case the data is the data is rotational in nature. So in case we are picking a subset which is not really random, and we pick the subset where the rotation part is lesser, then it'll perform suddenly better than the other one. Okay, good. The other question from Noor is, please explain the point two. Okay, I'll explain this with the visual. So let's say we have this data, right? And if this data is like vertical, the decision tree will be really happy. But the moment you rotate the data a bit, you rotate the data a bit like this. So we have just rotated the data a bit. Now, suddenly the model becomes really complex. Suddenly the model becomes really complex. Okay, so you can see that just by rotating the data by 45 degrees, the overall model had changed. While had it been regression or the standard linear model one, it will be the same line here and same line here. There won't be much of a difference. So model is sensitive to the rotation in case of decision trees. All right. Was he able to answer your question, Noor and Ross? All right. Great set of questions. So that was about the decision trees. Okay. So basically here So a question from Noor. So in practical world, we should normally avoid decision trees for regression. Not really. You could use decision trees for regression, and you should generally leave it to your cross-validation and grid search. Okay. Okay. So what does it mean by rotation? A practical example would help. Okay. So okay, that's an interesting question. So let me think, or you give me a suggestion that what does rotation mean? So rotation, let's say we are doing simple image recognition. Okay. Here, the feature like x-axis, y-axis can be correlated quickly with the normal physical axis of in image recognition. Okay. And we are trying to separate something. So if we just tilt an image a bit, that could be a quick example. Here, the features x and y, again, if let's say, okay, and so probably if we have some data and we are projecting on it on a certain angle, then also the rotation will happen in X and Y. But I think the easiest way to understand it is, imagine that there is an image which has X and Y coordinates, and we are trying to predict some value. This can be actually correlated straight away with the image. So so okay, let me just think. Um, if anybody else could come up with the suggestion, that will be great. So basically, what is the practical significance of rotation in terms of features? Okay, so what does rotation do to say x and y? It basically, so for the same data point, we have moved it a bit, say at certain angle, basically multiplied with, okay. So basically the two features x and y are changing because of the rotation in data. Okay, so let's say when we are looking at certain data points, and how should I explain that? Let's say we are having some data set and we are projecting the data and when you project, then the values just because of change in the projection, we'll get a different values. Okay, I'll think over it. Probably the easiest example is the image recognition, but in practical world there could be many scenarios, right, when the data is radial and things like that. Okay. All right. So yeah, good question. So we'll keep in mind that the rotation, how does it matter? Though it looks very clear and easy in case of image recognition or in case of the normal um, normal geographical figures, but for, let's say, data coming from an equipment, what does a rotation mean there? Okay. Good. All right. So that's pretty much on decision trees. So decision trees are powerful in summary, just that are uh, decision trees are very sensitive to rotation, and small variations in data changes the decision tree very easily. And decision trees are also very prone to overfitting the data. All right, so that was decision trees. Now, the next point that we would like to discuss is the ensemble. Okay, the first chapter in second chapter, the end-to-end project, the model that won was decision tree ensembled. Okay, decision trees, which is ensemble decision trees, is nothing but random forest. That's what we are going to do. So, so the decision trees are really powerful tools to solve many problems, as we saw in the chapter one, as we saw in the chapter two end-to-end project. Okay, so now, so this is an interesting topic. It is not a specific algorithm that we are going to talk about. It's just one strategy. It's just one strategy by gathering other existing logic. A question from Intel: is decision tree regression linear or nonlinear? So that's a very important question. So the linearity or nonlinearity doesn't matter in case of decision tree. Okay, the linearity or nonlinearity doesn't matter. Basically, when we were using the mathematical equation, then the linearity was of significance. But in case of decision tree, it's we can't say whether it's linear or nonlinear because the criteria is completely different. Okay. Okay, let me give you the slides. Okay, keep the slides with you, and right. Okay, now, okay, yes, a question from Inta was, how does it do the prediction? Okay, so the way it does prediction is, once it has prepared the tree like this, once it has prepared the tree, where did it go? Okay, let me just see. All right, let me go back to the decision trees. Okay, so the way it will do the prediction is, let's take this case. Okay, let's say let's say it has prepared. Are you asking about the regression at decision trees only? Regression with decision trees only, Binta? Or classification? Let me just, or you are asking about ensembling? Okay, let me just explain. Good. Okay, so we have, let's say this is our model. Okay, this is our model. Okay, let's say this is our model. So let's say this is prepared. It computed all these lines, prepared the tree, and we want to do the prediction. So we'll have to take a look at the tree, how it looks. Okay, how it looks. So we'll have to present it like a tree to give that answer like this, right? So oh, we did earlier we prepared this, right? Yeah. Okay. Yeah. Let's say this is the tree that is prepared. This is depth 2 and this is depth 3. Okay. So this is the tree that has been prepared. Now we want to do a prediction for what value? And let me just see. Okay. Let's say, all right, let me just fix the code to back to where we were. It's a supervised learning. Okay. Now, let's say we are saying here that predict this value. We are asking tree 2 to do the prediction for this, right? This value. Or let's say we want to predict for 3 or say 40. Okay. So what value did we get? 0.0844. Okay. That's the value we got. Now we come down and see if it is really giving that value. So zero point 0.4, it gave us 0.0844. Okay. So here let's take a look at this tree. We can generate this, right? Let me just generate this. Okay. I'm trying to generate it the way we did yesterday. Why it is only one label? Uh-oh, here. This should be 3, right? No? Oh, here. Okay. Now you can see that. So what we're trying to figure out whether for this value, it'll give this value. Okay. So 0.04, 0.04. So x is less than or equal to 0.197? No, right? So we'll go to the right. Here, it's a false. So is it lesser than this value? No, right? And okay, so this is lesser than this, yes. Okay, sorry, I think, yeah. Our value 0.04, oh sorry, I think, yeah. So we're talking about 0.04. It is lesser than this, true. So we went to this direction, which is lesser than that value. Okay, now further it's checking whether the value which we are looking for is lesser than or equal to this. So our value 0.004 is lesser than this. Okay, so here we are. Now we are saying whether it's lesser than this. Yes, greater than this is this. Okay, so you can see that the value is 0.947, right? 0.947, correct? So here, this is how it will do the prediction. Is it clear? No. For 0.004, first it will come here, then it'll realize that it has to go this side, then it'll go this side, and then it'll predict this value. Okay. For training, it'll keep on splitting the data and create the tree. And once it has done that, then for prediction, it'll basically compare whatever we have done there. Okay. Now this value is the average value, the mean square error at every point. The way it has computed this value is by dividing the data at certain point, finding that value. This is that decision boundary. Okay, so it's basically returning that decision boundary. Okay, the way it has computed it, first it divided the data at certain point where the error on right and error on left, the total, the weighted average of the two is minimum. That's what it kept on iterating through this data. It kept on iterating through this data. Now, and that's what it did further and further. Okay, so it basically calculated the decision boundary, and for that value, for this value, it basically further, it further divided it into other parts. Okay, that's what it did. All right, does it make sense? No. So this value is this decision boundary. This value of y is this value here. Yes, it works on large number of features. You can add more features and it'll work well in the same way. All right. All right. So yes, it does work well on large number of features. Remember, in the first session, there were in the end-to-end project, there were many features. There were many features, and it was able to do really well on those many features, right? So yes, it works well on large number. When we say large number of features, um, the complexity is something that would answer that question better. The complexity of this is m into n. So I will show you the complexity of the CART algorithm, right? So if n are the number of features, then it works well. So you can see that the it works pretty well on large number of features, okay? While if m is the total number of instances, the complexity is m into log m. The complexity is proportional to m into log m, okay? While it is linearly dependent on the number of features. Wonderful. Great, great set of questions. Should we move on? All right, let's start the ensemble learning after the break. So we'll do a break for 10 minutes. All right, so I'm back. Should we start now? Hi, everyone. Should we start now? Are you able to hear me clearly? Are you able to hear me clearly and see the screen clearly? All right, wonderful, wonderful. So let's start. Okay, this session we will learn about ensemble learning and random forests. Random forests are part of ensemble learning, a group of predictors. So we are going to use a term called predictors. Okay, in ensemble learning, we're going to use multiple algorithms together in order to achieve the results. Each of the algorithm or uh, each of the each of the algorithm is will be called as predictor. Okay, so therefore a group of predictors is called an ensemble, and thus the technique is called ensemble learning. Ensemble learning algorithm is called an ensemble method. Okay, so the winning solutions, you'll be amazed to know that most of the winning solutions so far on Kaggle and in real life are always ensemble. Okay, ensemble methods are the most practical ones and are the most winning algorithm. Say, for example, the algorithm that won the Netflix $1 million flagship competition was ensemble learning. The one, the end-to-end project that we did, the one that won was ensemble learning because random forests are nothing but ensemble learning method. Okay, so ensemble learning is something really really important. and we're going to talk about various techniques and various ways of ensembling. We're going to we're going to uh, talk about these topics. Okay, we're going to go with various voting classifier. Then we'll talk about bagging and patch pasting, and then we'll talk about random patches and random subspaces, and then random forests and boosting and stacking. All right. So suppose you ask a complex questions to thousands of people, of random people, then aggregate their answers. In many cases, you will find this aggregate answer is better than experts' answers. This is called the wisdom of crowd. In many scenarios, a weak algorithm or weak predictor, a group of weak predictors turns out to be a very strong predictor. Okay, so we'll prove this part that how an individual how the how an ensemble, let's say there are three algorithms which are really weak, which are basically able to predict to some extent. When you ensemble them, the overall outcome is far more superior than individual. Okay, so so if we aggregate the predictions of a group of predictors, such as classifier or regressor, you will often get better prediction than with the best individual predictor. So the combination is better than the max of it. Combination is better than the best. Okay, that's the important part that I want to express, that the combination is better than max or better than the best. Okay, so so all right, so this is called an ensemble. Okay, now suppose you have trained a few classifier, each one is achieving about 80% accuracy. Okay, let's say you're predicting something, and you have three classifier. One is logistic regression, other is SVM classifier, and third one is random classifier. Okay, we'll skip the KNN right now. That's another classifier we have not studied yet. So let's say we have a decision tree, SVM, and logistic regression. Now, each of them is having 80% accuracy. Now, if we ensemble them on a given data. Okay, let me just go back. So let me just put the problem forward properly. Suppose you have trained a few classifier, each one is achieving about 80% accuracy. Suppose you have logistic regression, you have SVM, or you have, say, third algorithm called random forest. Now each one is having an accuracy of 80%. This is 80%, this is 80%, meaning out of 100 times, it is giving the correct result 80% of the times. 80 times of out of 100 is giving the correct result. Same is here, same is here, same is here. Okay, now the difference is that uh, they are giving different results at different instances. Okay, say let's say we have 4 inputs. So for first 3 input, this one gave a correct result, while fourth one it gave an error, it gave a wrong result. Like this one is, say, giving the correct result out of 4 on the last 3. First one it's giving a wrong result, and let's say this one again it's giving a good result on first, third, and fourth. For the second one it's giving wrong result. So we have, let's say, these. Now suppose each of these are having accuracy of 80% on the data. All right. Now, is there a way to achieve higher accuracy using these given models? Can we achieve higher accuracy? Anybody? If you have to use the 3 algorithm, can we use them in conjunction and achieve better accuracy? How? Okay, thank you, Noor, for putting the marker. Yes. So how will we achieve a better accuracy by using, say, multiple of these? Any suggestions? Yes, we could add dysenteries also into this. We could actually have added dysenteries here instead of ensemble. Yes. Okay. So let's just keep the ensembling. Ensembling is quite a common sense thing. So and yes, the accuracy of various models is pit against each other for the data. That's right. Okay. Pradeek's suggestion is that we could use decision trees for identifying the model to use. Very interesting. Very interesting. Okay. Okay. Bindav's suggestion is the combination of best feature from each classifier. Okay. Okay. That's also very important answer. We'll talk about this part. We call it random patches. Okay. We should find where each model doing the best. Okay. Okay. Very good. Very good. Very good. Yes. So, okay, we want the overall better accuracy and of course on the test. If something is giving better accuracy in training, we could just do regular, you do overfitting and we'll get the 100% accuracy. Okay. Okay. So can we, question is bigger, that let's say each of these algorithms is giving 80%. By combining them in some way, can we achieve better than 80%? All right. So let's just take a look at, say, the same example that we are talking about. Okay. So we have this example. Now, yes. Okay. Imagine that logistic regression here is giving us, say, let me just do it in this way. I'll just take the first layer. Okay. Let's just take a case of this one. Okay. So imagine that, yes, we could also pipeline algorithm. Very good. Very good. Yes. So we could do many things. I think we got very good answers. So we got very good answers, and these are very, very important. The ones that all of you have answered are actually the things that we're going to talk about in various ways. So here in random patches and random subspaces, we talk about picking up features and then pipelining and algorithms. That's the next thing. That's where we do boosting, and there were a few more very good answers from you. So we will learn all of these parts as part of ensembling. Okay, so great, great. Now, so I was trying to explain that just by using very simple technique, I can prove that by combining multiple algorithms, we can achieve very great results. Let's say the accuracy is 80%, meaning it gets it correct four out of 5 times. It gets correct 4 out of 5 times. Okay, so let's say these are those. Okay, so let's say this is the wrong one. So this one was correct first 4 times and wrong on the 5th record. Now, let's say the stream classifier gave us wrong result in first case while it gave correct results on these, because they are having some kind of 80% accuracy. While say third algorithm was performing really great on this. Okay, the third algorithm was performing really great, but did give us wrong result here. Okay, and say correct, let's say here it gave a wrong result. Ouch. Okay, so all right. So let's say this is the scenario for first instance. So for first instance, second instance, third instance, and fourth and fifth. Let's say this is the scenario. Now, if we just, pick the best out of this, we combine all these algorithms, ask for their answers, and ask them to give the best, and then ask all these. Let's say we're predicting for some value, and logistic regression says yes, SVM says no, and random says yes. Okay, let's say we ask the question from these, and what we do is we pick the one which is in majority. So the ensemble one will give correct in this, correct in this, correct in this, correct in this, and correct in this. So you can see that ensemble learning basically basically is able to come up with the overall the 100% accuracy. Okay, so logistic regression gave some prediction, SVM gave some prediction, random forest gave some prediction, and what we did was we picked the prediction which was most common out of this. Okay, this is the voting classifier. Okay, this is the voting classifier that we learn in ensembling, voting classifier ensembling basically. So what we do is we pick the one which is the majority. Okay, so and so on. So the effective accuracy is improved. All right, so the accuracy of this one would be like 100%, while the accuracy of this was 80%. The accuracy of these all was 80%. Okay, does it make sense to you? Okay, so it's a very simple, the very simple way is to create a better classifier is to aggregate the predictions of each classifier and predict the class that gets the most votes. Okay, so that gets the most votes. If all of these had the same behavior, all of these algorithms had the same behavior, then we may not get the right results. Okay, we still will get say 80% here. Okay, all right. So so this is called the voting classifier. So what we do is we pass the new instance through all the diverse predictors, and then whatever is the prediction, we pick the majority. Okay, so here the prediction of ensemble will be decided by the votes from all the classifiers. Okay, the class that gets the highest vote is the final output of the ensemble. This is called majority vote, or it is called hard voting classifier. Okay, here it is simply based on the votes. It's simply based on the votes. Okay, it's simply based on the votes. So and the problem with majority votes is generally there are high chance of tie. Okay, what if two of them says yes and other two says no? Which one should we pick? Right? There are chances of tie, and therefore hard voting classifier is seldom used. A question from Kamal: how can I do that to predict? So basically, we trained 5 algorithms on the same data. We ask all 5. While predicting, we use the predictions of all, and we pick the majority. That's what we do. And in case of regression, all we did do was maybe pick the maybe average, and that's what we learn as we go ahead. So we can't do that for regression. We can't do the hard voting for the regression. We can do it for the classification. Question by Pratik is who does the voting? Okay, so basically, when let's say we have 4 algorithms, okay, we trained all 4 parallelly, right? So we created one with SVM, other SGD, other say one SVM, other SVD, other say using the decision tree, and other some say using the what was the one? So we have used SVM, linear model, and the decision tree. Let's say we have just 3. So we trained all of these algorithms in parallel. We feed them data and let them learn. And once they finish the learning, then we call fit method on all 3. Call the after we have called the fit method, we call predict method on all 3. Okay, and whatever is the majority, let's say first one is saying okay, if we talk about our example of say MNIST, right? Remember the MNIST there. So we gave the digit to each of the algorithm and said that is it 5 or not 5, and 2 of the algorithms said it's 5. Okay, then the result, since 2 out of 3 is majority, we say that the outcome is 5. Okay, outcome is 5 instead of saying not 5. So that's what we do in case of voting classifier. Okay, so we have the digit here, image here, we pass through first classifier, it said yes, it is 5. Okay, or okay, let me just stay in the touch. We gave the image here and it said okay, this looks like 1. Second one said this looks like 1. Third one said no, it looks like 2. And fourth one said it looks like 1. So the majority voting means that we pick the one which is having the most frequent observation. Okay, a question from Noor: does it need to be separate algo always, or can it be 2 customized versions of the same algo? Okay, so does it need to be separate algo always, or can it be a 2 customized version of the same algo? So basically, it is not, it doesn't need to be a separate algo. We could also write our own function saying, call all of these, gather the result from all of these, and then whatever is the result, we can save it and compare. Okay, now question is that, can we do better than the scikit-learn? Yes, we can do better, but there are many optimizations that scikit-learn has done. For example, one of the very good uh, optimizations that scikit-learn has done is it runs all these algorithms in threads in separate CPU, which means that all these algorithms can be trained and used for prediction in parallel. Okay, so in parallel using multiple CPU. So that way, the overall performance actually comes out to be the same. The time it takes would be similar. All right. Now, so it looks somewhat surprising. The voting classifier often achieves a higher accuracy than the best classifier in the ensemble. In fact, even if each classifier is a weak learner, meaning that it does only slightly better than random guessing, then ensemble can be a strong learner. So even though your algorithm is just slightly better than the random guessing. Still, if you ensemble them together, the overall outcome is actually pretty good. Okay, so if you have sufficiently diverse weak learners, then your outcome will be great. The important point here is diverse. Okay, even if diverse as in they should not all be giving the same result. Imagine they all had the same result, the accuracy will still be 80%. So if SVM also said correct, 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 and wrong, and random, the third one also said correct, 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 and wrong, then also we will get the 80%, not 100%. Okay, so it has to basically, it has to be weak learner. Again, it has to be slightly better than random. Okay, slightly better than random and diverse, the important part. So Kamal's point is that this implies that democracy should work. Okay, so yes, yes. Okay, this implies that the democracy should work, provided that we are diverse, as in we have our own opinions and understanding, and we are diverse, not impacted by common media, then the chances of electing somebody would be a better decision. Okay, and so unless the Russians interfere, yes. So okay, you know the you know the thing. So basically, the moment the a lot of marketing and media comes into play, the so-called diverse opinion becomes kind of less diverse, and because of which the outcome of voting isn't really smart. Okay, so so how is it possible that ensemble performs better than the individual classifier? Okay, so a question from Kamal is, can that happen here also? Yes, it can happen. The fact here, if let's say our models that are being trained here, they all are kind of, let's say we did not have our data sufficiently randomized. Imagine that we did not randomize our data and we are having logistic regression parallelly. Okay, so there what would happen is all the algorithms will give the same results. Okay, if the data is not randomized, or the the we are using the same kind of classifier, then the chance of the outcome being less diverse is very low. Okay, so it can definitely happen. All right, great. Now, how is it possible? Again, this is a very hard to digest, that uh, the outcome cannot be better than the best. Okay, so we'll try to prove it in another way. Suppose you have a slightly biased coin that has 51 chances of coming up heads, okay, and 49% chances of coming up tails, meaning we have a predictor which is 50% right, 1% right, and 49% wrong, okay, 51% right, 49% wrong. So what we are saying is, can the weak learners be used to do the prediction? Okay, so let's say we have a biased coin, and the coin basically gives correct predictions, meaning it shows head 51% of time and 49% of time it shows tail. So if you toss it say 1,000 times or 10,000 times, you will you will start getting majority at a lower the chance of getting majority becomes higher and higher. Okay, so for example, if you toss it 1,000 times, you will get around 510 heads and 490 tails, and hence the majority of the heads Is it clear? So there's a biased coin, 51% time it shows head and 49% times it shows tails. Okay, so when we throw this coin 1,000 times, there are 100% chances of getting 510 heads and 490 tails, and hence the majority of heads, right? So if we just take a look at it now, if we do one toss, there could be it was one head and there was no tail, and there could be another thing that we get a tail. So the probability of each one is getting the head is 0.51, getting the tail is 0.49. Okay, all right. So the point we're trying to do is that imagine that the coin is your predictor. Okay, it's right. It's right 51% time, which is when it gives head, it means it's right. When it gives tail, it's wrong. So 51% time it is right, and 49% of time it is wrong. Okay. Now, if we the point we are trying to prove is a very important one. When you toss it around 1,000 times, you will get the majority of heads. Getting majority of heads becomes 75%. Getting majority of heads becomes 75% instead of 50%. Okay, like here when you throw one head, well, once, getting majority of head is 51% time, while when you throw it sufficiently large number of time, getting head as majority keeps on increasing. Getting head as majority keeps on increasing. And that's the same case with our ensembling, that when we run the same algorithm or or run a similar thousands of algorithms parallel, even though they are giving, say, correct results only 51% time. Okay, only 51% of time. Even though if we ensemble thousands of such algorithms together, after a point of time, after a point of time, their accuracy will grow to 75%. Okay, that's what we are trying to do. So let's say we have a single coin. The chance of getting head is 51%, and chance of getting tail is 49. Now, if you have two tosses, you did two tosses. There could be that you got both the heads, head followed by another head. The chance of this is how much? 0.51 into 0.51, correct? And there could be another scenario that we threw the tail, through the we did a coin toss, we could get tail and tail, right? So H, 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 and TT. The chance of first time tail coming is 0.49, and second time, both the tails, the chance of that is 0.49 into 0.49. Okay, now when we throw a coin, when we throw a coin twice, so okay, so okay, so here you did a coin toss. Okay, you did a coin toss, it is head, and here it could be head, head, tail, tail, right? Or it could be head, tail, and tail, head, right? So this could be one, this could be two. Okay, there could be these four total scenarios. When we do the coin toss, there are total four scenarios. Okay, you first time through it was head, and then second time you threw again, it was again head. The chance of this is how much? 0.51 into 0.51. Okay, and chance of both being tail is this much. Chance of head followed by a tail is chance of head followed by tail is 0.51 into 0.49. Chance of tail, chance of head followed by tail is 0.49 into 0.51, and chance of tail following head is 0.49 into 0.59. So the overall will be this. Okay. So will be sum of the two. Does it make sense to you? No? So probability of getting one head and one tail is this much. Probability of getting both tails is this much. Probability of getting both heads is this much. Okay. All right. Now further, if we have total number of three tosses, there could be all three of them are head. The probability of that one is this. The probability of all three tails is this. Probability of one head and two tails. There could be three possible combinations of this. There could be first tail, then head, then tail, right? So there could be in this case scenario, what are the possibilities? You get one head and two tails, right? So first you got tail followed by a head, then tail, then you got head, tail, right? And it could be tail, tail, head. Okay, it's not looking good. So there could be, okay, so what could I do? Okay, there could be a scenario here of tail, tail, and head, right? So there could be three scenarios. So, and similar is the three scenarios here. The three scenarios here could be head, head, tail, right? Then head, tail, head, because one head and two tails, and tail, head, head, right? So the probability of this one is this much. Okay, why? Because this one is 0.51, 0.51 into 0.51 into 0.49, 0.49 into sorry, 0.51 into 0.49, 0.51, 0.49, 0.51, right? So you can see that this these are the various probabilities. Now please note that what are the situations where head is in majority? This is majority, right? Correct. And when you see that we are looking for the situations where head is in majority, right? We're looking for these two cases. So when you sum it up, the probability is more than 50%. Okay. When you sum these up, probability is more than 50%, 51%. I'll show you that. So we're talking about these two cases, right? 0.51 cube plus 0.51 cube. So not here, I'll just write here. So the overall probability was 0.51 cube plus 3 into 0.51 square plus into 0.49 into this, right? So you can see that the probability is actually quite high. Okay, so you can see that probability of majority head is more than 51%. And as more and more tosses happen, the probability of majority would keep on increasing. The probability of majority would become the probability of majority heads. The probability of majority heads would become more and more. Okay? That did make sense to you? So as the number of tosses are increasing, as number of tosses are increasing, meaning more ensembling is happening, the the chance of heads or is chance of majority correct is increasing. So even though it was slightly better than random, the coin was slightly better than random, 51% instead of 50%, still after sufficient number of throws, the chance of majority would grow really high. So yes, that'll be after probably infinite number of throws. Okay, so what we are looking for is a majority. Okay, so by combining say 1,000 tosses, we are basically bringing the accuracy to 75% from 51%. All right. From this observation, we find that the possibilities of coin tosses follow the binomial expansion. So if we toss a coin n number of times, the probabilities will be in terms of binomial expansion. Here, a probability of head and B is the probability. Here, A is the probability of heads and B is the probability of tails. That's what it is basically. Now, let us find the probability after tossing the coin n times. So basically, that's what we have done here. So after n times, if you are looking for majority, that means the right. So we are looking for the head to be in majority. The power of A should be more than the power of B. In this, right? So if you see A, B square, B square, A, and so on. So it's basically this. So for the for the majority, all we are looking for the numbers where the power of A is more than the power of B. Okay, that's what we're looking for, and so on, right? So in simple words, that's the derivation further. So if we do thousand of such terms, if we do 1,000 of coin toss, we are going to get an accuracy of 72.6%. Here, hence, the combination of 100 classifier with 1,000 classifier with only 51% accuracy, the combined accuracy is over 1,000, over 72.6. Okay. So a point from Ross is that a majority vote of fairly accurate models lead to the right prediction versus being a really bad data scientist and creating majority of bad models. Okay. Okay. So yes. So even if we created majority of really weak models, not bad models, weak model which at least do some prediction, some amount of accuracy they have. Okay, if you put them sufficiently large, you might end up with good accuracy, provided you use things like voting classifier. All right, good, good. That's a good way to put it. All right, so again, the right. So no, actually, this is true in the practical. Okay, this is true in practical. So we can actually get really good accuracy after a point of time. So I'll show you this actually. This is something I would love to show you. Okay, after this. It's actually very practical to have combining, right? So in practical, the thousand of right, in case of random forest that we did earlier, we were actually using thousands of decision trees under the hood, and that's how it worked. Okay. So yeah. So question from Noor is, but to gain 75% of majority, we would need 1,000 weak models with 51% accuracy. But good part about our case is that our weak models, even the weakest models, are actually better than 50%, right? Our weakest models, whether we use SVM, whether we use anything, they are better than 50%, 51%. Therefore, the accuracy is going to be really high for them. Let's say our this was, say, okay, let's say 70% was our coin toss resulting in. So our after 3 coin toss, the probability is going to be 80%. You see that? If our model is, say, 70% accurate, and we try it 3 times on separate random data, getting the correct results become 78%. Okay. All right. So therefore, it is very much practical and achievable. Okay. So again, if you perform 10 series, if we do the 10 series of coin tosses for 10,000 iterations, the probability of head reaches 51%. Okay. So so this is the same thing put in the diagram. So as the number of tosses increase, the ratio of head approaches 51%. Eventually, all 10 series end up close to 51%, that they are consistently above 50%. Okay, so the point here is that they will all be consistently correct, meaning consistently above 50%. Okay, so here is, I think we can skip this part. Okay, now this is far better idea to try to make our own voting classifier. Okay, so imagine that we created our moons dataset. You remember the moons dataset? Let's just go over to the, where is our, okay, I think maybe I'll have to pull it. All right, it is not there. CDML. All right. A question from Kamal is, in the above example, let us say there is another coin which gives head 80% of time. Then if we use voting classifier to add to this one coin and 99% coins which give, okay, in the above example, let us say there is another coin, okay, which gives head 80% of the time. Then if we use voting classifier to add this one coin and 99 coins that gives 51% times head, what would be the final outcome? Less or more than 80%? It'll be actually slightly more than 80%. No, it'll be, okay, the probability will be different. It's a very interesting question. It's a very interesting question. So the probability would be worse than 80% actually. Okay, the probability would be worse than 80%. I think we can do this at later point of time, but because majority is basically kind of on the random, and therefore majority would give the okay. It should be better. Let's say there are 2 coins. Okay, let's say there are 2 coins. One gives head all the times, okay, and the other one gives say tail all the time. So let's say, Okay, let me just show you. Okay, it's an important question and will be really hard to derive. It took me some while to derive this point with the coins. Okay, though it looks simple. So now coming back to say two coins, right? One coin, two coin, and say three coin. Okay, and let's say all of them give basically head, tail equal. Okay, tail, head, tail, right? This is tail, this is head. For each tail, this is head, this is tail. Okay, let's say these are both random in general. Okay, while this one is 80% biased or 100% biased, let's call him 100% biased. Okay, so it always throws the head. Okay, it always throws head. So if we do the voting classifier on top of it, it says head, it says head, and it says head, and it says tail. So, so here you can see that the overall, the overall result is say 80% or 75%, right? 75%, correct? So this was 100% accurate. This was random. This was random. So the result is 75%. All right. So so in general, yes, if the number of how should I say, the in this particular case, the the accuracy of the overall model is brought down a bit. The accuracy of overall model is better than the random, but it is worse than the best. Okay, so in this particular case, where we have two extremes, okay, two extremes, and so on. So yeah. So if they were 50%, 51%, correct, 51% of 51% of 51% right, what will happen is this will be a little better than 75%. Okay. Okay. In the same way, in the same way, if we have say thousands of such models, okay, or maybe 10,000s of such coins being tossed parallelly, then the accuracy will be close to say 100% or 90%. All right. I hope this example clears it. Okay. A question from Kamal is maybe the rule is closely ensemble only closely performing models. If one or few are very much better than the others, then we should just use that. Okay, so good point, good point. So we should use yeah, we should use, these kind of extremes aren't generally there in the algorithms. Okay, the algorithms are, most of the algorithms are better than the average. Okay, so, and of course, a better performing algorithm is definitely a better candidate. Okay, but if you have another one which is slightly is basically underperforming algorithm but is diverse, so you basically look for diversity as well as look for accuracy, both the things you look for algorithms to ensemble. All right. So in general, yes, it makes in general, most of the algorithms, it makes sense to ensemble them, but you would like to ensemble the algorithms together, which are diverse, as well as basically which have very different behavior, like decision tree and linear regression. Both are very different behaviors, correct? Therefore, their results could be really different. Therefore, it makes sense to ensemble them together. So along with accuracy, we also look for the diversity. So yes, we would generally be ensembling the closely performing models and definitely not the random ones. Okay. All right. So next question is from Noor. So what I understand is that before ensembling, we should try and achieve best training models, then ensemble to get the maximum output. That's correct, Kamal. Actually, I'm not able to understand what is diversity mean in terms of practical terms. In terms of practical terms, diversity means the result, the one that I was talking about here earlier, that if all three of them basically gave the same result. Okay, we showed the same image, all of them said yes, then all of them said yes, and then all of them said no. The outcome will be 80%. So if let's say it's the same algorithm trained on same data set, then the result will be exactly identical. So it would not make any sense to ensemble together the same algorithm trained on same data. Okay, so that's what diversity means. All right, different training set or different sample, different hyperparameters, and so on. Okay, all right, so let's generate some data. This is the moon's data set. So I was trying to find out what happened to, yeah. Okay, so good. So it has pulled the data set. Now it should be there. What was the name? Ensembling and random forest. Okay, let's start. So this is not really required. This is where we are computing the probability of 500 coins. So here is, it's basically not 500 coins, it's basically for 1000 coins in the cases of majority. That's what we have done. And so you can see that when you do you throw a biased coin 500 1000 times, the majority had the probability of majority has 73%. So by ensembling the coin toss together, we are able to bring the chances of heads from 51% to 73%. Okay, now uh, I think this is what we have done here. That's okay. Let's just talk about later. I think you can figure it out by yourself. And let me just move ahead. Okay, now let's generate some data. So this is our random generated data. This is from the make moons method from datasets. So it basically creates some kind of a random data. Now, it's not entirely random. It kind of creates these complex weaved in difficult to separate kind of a data. Now, here, what we are doing is once we have created this data set, now we are training three classifiers. First one is logistic regression. the one that we studied in the classification. Second one is not yet studied. It is random forest. Third one is SVC. Okay, so this is the support vector machines classifier. And then what we are doing is we are creating a voting classifier based on these three algorithms, these three algorithms that we're going to use. And then, we are fitting it. Okay. We ourselves could also do that. We also could call this fit, this fit, this fit, and then we find the average of them. Okay. All right. Now, so this is the voting classifier. We can also do that. So we have done it here. So for CLF in this, CLF dot fit this, predict this, and then print the results. Okay. So voting classifier here, voting classifier basically gave us this much results. Okay. So you can see that the result of logistic regression was this much accurate, 86%. Random forest was 87%, SVC was 88%, and voting classifier is approximately 90%. Okay, why? Basically, it's using the same three algorithms. Okay, so each instance in the prediction is passed through each of them, and then it is measuring the accuracy of each of them along with the majority predictions. Okay. Okay, this is the name that we are giving it. So the way we call voting classifier is with an argument called estimators. Estimators expects you to give an array of tuples. Each tuple has got a string and then the algorithm. Okay, then the algorithm. This is just for reference so that we can take a look at the results of each one. Okay, so you can see that the accuracy is improved. Though it is improved from the maximum by just 0.1%, but it has improved. All right. Great. All right. Just like we did for pipelining. Thank you, Saruk. Now, here we basically used a term called voting hard because we are strictly following the votes. Okay, we're strictly following votes. So, okay, so hard voting is when we consider only the final output of each classifier for our voting. This is called hard voting. All we did here was, all voting classifier did was, it basically for every instance in the prediction, every instance of say X test, okay, every instance of X test was passed through each of them, and whosoever gave the, whichever was the majority was considered as the outcome. And then the accuracy was measured on the outcome. All right. So this is called hard voting. So on the other hand, we have something called soft voting. If all classifiers are able to estimate class probabilities, they must have predict probability method. Okay, so let me come back. So instead of hard voting, we generally prefer the soft voting. Instead of just considering the outcome, we consider the probabilities. Okay, we consider the probabilities, we sum up or average the probability, and that becomes the chance of the outcome. Okay, so this way the soft voting is generally preferred because hard voting had a chance of a tie and therefore may not give you a very good results. So in soft voting, we basically sum up the probabilities. Let each algorithm predict and give the probability. And how do we do that? We use a method called predict underscore probe A. Okay, probe A method gives the probability instead of classifying it right away. It gives the probability of a particular instance being in which class. Okay, so it gives the probabilities of an instance being in each class. Okay, so most of the algorithms have predict underscore prob A method, just that some of them do not have the probability associated. For example, SVM does not have the probability associated. So, but you can enable it by calling a variant of SVC. Okay. So all you do is, in case of soft voting, all you do is basically call all the algorithms, get the probabilities of all classes, sum up the probabilities of individual class, and find the average. And then based on that probability, you take the call. Okay? Based on that probability, you take the call. So it often achieves higher performance than hard voting because it gives more weight for high confident votes. So all you need to do is replace voting equals hard to voting equals soft, and ensure that all the classifiers that you are passing to the voting classifier can estimate the class probabilities. Okay, otherwise it'll throw an error. Okay, a question from Ross. It seems logical that ensemble learning plays an important part in reinforcement learning. Yes. All right. So, okay, okay. Let's verify the fact that soft voting often achieves higher performance than hard voting, and we'll find that the soft voting classifier achieves over 91% accuracy. Okay, here we achieved 0.89. Let's try that. And this time, let's see. You can see. So the soft voting classifier achieve 0.02%, zero point zero 0.02 more accuracy than the best. You can see the difference. All right. All right. So a question from Noor is, I did not get the soft voting part as to how it will classify. Okay. This is, so accuracy with hard was how much? This much. And accuracy with soft was this much. So this is basically as compared to 0.896. 0.896, and here it is 0.91. So you can see a 0.02 difference, right? There's a huge difference between the voting classifier and the other one. the hard and the soft. Okay, a question from Noor is, I didn't get the soft part. So the way it works is again, let me just draw it here. Imagine which all algorithms did we use? We used logistic, we used random forest, and we used SVC. Okay, so let me just draw it. Okay, let me just draw it. Say this is our logistic regression. This is SVC. This is okay. And so logistic, random forest. Okay, this is, let's say, logistic. Okay, and random forest and SVC. Let's say these are the three algorithms. We trained all three of them. Now we are calling fit method, and we're basically using the predict probability. They provide a predict probability. We are passing, let's say, an image. Okay, let's say an input image to just predict. So, and similarly, same input we are giving to all of them. We are giving same input to all three of them. Okay, now we are asking for something called predict probability. Predict. Okay, that's what we are asking to do. All these three methods, that's what we are calling. So instead of it saying yes or no upfront, okay, it is what was the value? What was the name of the classes that we were passing in the Moon's dataset? Okay, what is the Y? What is the Y? Okay, so instead of giving the verdict, it's giving the probability. Okay, in our case of 505 kind of situation, here it'll be okay, this is 0.1 and this is 0.9. Okay, this one is giving us that, let's say. Okay, so all of these would give some kind of a probability. Okay, all right, let's say this. So when we pass the input, it gave us a probability of various classes. Okay, and then what we did was we basically averaged these values. We averaged these values. The average of zero point 0.1, zero point 0.2, zero point 0.3, it's going to be how much? It's going to be 0.2, right? The average of 0.9, 0.8, 0.7, the average is going to be 0.8. So this is the accuracy, this is the result. Now, based on this, now probability of the second class is higher, and therefore the prediction is this. If let's say these classes are, let's say, this represents 5, okay, this represents 5, and this represents not 5, okay? So what's the verdict? Verdict is it's not 5. Okay, whatever image we have passed. Okay, did it make sense to you? So we did the average of 0.1, 0.2, 0.3. Similarly, we did average of 0.9, 0.8, 0.7, and that's the outcome. And this we are going to do for all inputs, and then compute the accuracy. Okay, then compute the accuracy. A question from Ross. Let's say you have three probabilities. We have three classifier and we have 0.45, 0.45, 0.9, correct? Then the hard voting would give you the score of 1/3, 1 in the favor and 2 against. Yes. Correct, correct. That's a very good point. So it will classify it as negative. That's right. That's right. Soft voting would give you the average of the probability, which is zero point 0.6, would be positive. Great, great. So yes. So basically, it's not only the voting, it's all also the intent. All right. It's also the intent, how convinced an individual classifier is. It's a very good answer. Okay. In this case, the hard voting scenario, it is going to be say yes, yes, and yes, and hence yes. But if this is say probability, it's giving the first one is giving us 0.45, 0.55, and so on. Okay, so let me show you. Imagine that I'll just take the case which Ross has given. It's a very good example. So let's say we have 0.55, okay, and 0.45, right? 0.55 and 45. And this one is how much? Let's say zero point 0.1 and zero point 0.9. Correct? So the voting classifier would see that, okay, majority is saying that this belongs to the first class, right? Majority is saying that. So the hard voting would give the result as the first class, which is 5. While the soft voting will give the result as how much? 0.5 plus zero point 0.5 plus zero point 0.1 is how much? Okay, so zero point 0.5 plus zero point 0.5, this is 1.1, 1.2, so this is zero point 0.6, and this is, okay, I think I'm making a mistake. So I have to divide this by zero point 0.4, and this will become zero point 0.6. Okay, all right. So you can see that as per the soft one, it is zero point 0.6. All right, sorry about the disconnection. So yeah, my network suddenly disconnected. Okay, let me, actually I must have missed at least 5, 6 questions. So could you just copy paste? So yeah, thank you, Noor. So yes, let me try to answer Binta's question. It should be 0.55, 0.45 for hard voting based on majority. So see basically, if you take a look at the individual instead of probabilities, if you take a look at this, it is saying that it is a 5. This is saying it is a 5, and this one is saying not 5, right? This is saying not 5. Correct? So if you see the majority is saying it's a 5. So hard voting is saying that it's a 5. While hard voting is basically counting votes. One vote for 5, one more vote for 5, while only one vote. So total 2 votes for 5, only one vote for not 5. This is hard voting. What soft voting is, we just sum up and compute the average. So zero point 0.5 plus 0.55 plus 0.55 plus zero point 0.1, which is 1.2 divided by 3 is zero point 0.4, and 0.45 plus 0.45 plus zero point 0.9, which is zero point 0.9 plus zero point 0.9, 1.8 divided by 3 is 1.6. So now, based on this, which has more probability? 0.6, 0.6 is more, which is not 5. The second one is not 5, and therefore, as per the soft, the outcome is not 5. Correct? Okay. So not as per the in majority, while counting majority, we don't look at the probability at all. We just look at the predictions of individual classifier and then compare. Great, great. So that was about the hard voting classifier and soft voting. All right. We'll continue from bagging and pasting in the next session. Okay. I hope this was useful to you. So we'll learn all other techniques of bunching other algorithms together or bunching the same algorithms together, whether sequentially, parallelly, how to pick the samples, how to, and all of that. We will do that as we go ahead. All right. So we'll continue from here. So in this case, the outcome is right. So no. So here, as per the soft voting, the outcome is not 5, while hard voting is 5. So we generally prefer soft voting because soft voting gives better results. Okay. And we can compare the accuracy by running the soft models, and that's what we did here. That's what we did here, and found that when we changed it to soft model. Here, this is the one which we did. So the moment we made it soft voting, what happened was we got better accuracy. So how is this accuracy computed? All of this X test is passed through the data, passed through all the classifier. Then the overall performance was compared with the actual, and that's how it clearly shows that soft voting is a better measure of performance. It's a better way of ensembling the algorithms together. Okay, if your algorithms can predict probability, then use the soft voting instead of hard voting. All right. If your algorithms cannot give you the probability, then you will be forced to use the voting classifier with hard voting. So thank you, everyone. We'll continue from bagging and pasting. I hope that this class is useful to you. I look forward to see you next week. All right. Thank you, everyone. Have a good day. Thank you, Balaji. Thank you, Bintao. Thank you, Gigi. Thank you, Kamal, Noor, Pratik, Ross, and Sharuk. All right. All right. Okay. So yeah. Bye-bye. Have a good day.